In this example, we're going to take a look at an application of our formula for average value of a function over an interval. Um, here we're given this model from biology that tells us that the velocity, which we're going to call v, of the flow of blood through an artery um, at distance x from the center of the artery, and if the artery has a radius capital R, that velocity is given by this formula. And in this formula, of course, x is the variable, r is again the radius of the artery, and k is a um, constant of proportionality that can vary depending on, I guess, the particular artery or particular animal. Um, and so what we want to find is what is the average rate of flow, um, what's the average velocity of the blood through this artery. So I've drawn here a really crude picture of an artery. Of course, that's going to be something like a cylinder, right? Again, here's the center, the central axis of the artery, the center of the artery. And in this scenario, the radius of the artery, that is the distance from the center to the edge of the artery, right, that is given by capital R. So this distance x, at which we're going to measure the flow of blood, of course, that has to fall somewhere between 0, because we might be right at the center of the artery, and capital R, because obviously the blood can't be any further distance, right, than the radius of the artery or away from um, the center of the artery. It's kind of interesting to actually evaluate this function at some values. For instance, if you evaluate it at 0, right, that would be the rate of flow of blood right at the center of the artery. That's at distance 0 away from the center of the artery, and that's an easy calculation. Of course, you're going to get k times r squared minus 0 squared, right? And of course, that just simplifies to k times r squared. So that's the speed of flow of blood at the center of the artery. But if you go out to the edge of the artery, so if you look at that maximum distance that the blood can be away from the center of the artery, so that's when x is capital R, and evaluate, well, it's also an easy evaluation. You get k times r squared minus r squared again, because we're going to substitute r for x, right? And of course, that is going to turn out to be 0. So that tells us that right up against the edge of the artery, right, the flow of blood is very slow. That's because, of course, there's friction, right, with the walls of the artery. So the blood cells, the plasma, and whatever else there constitutes the blood, right, that is brushing up against, right, the edge of the artery, so that's slowing it down. But in the center of the artery, the blood is flowing much faster. All right, but now what we want to do, of course, is find what's the average rate of flow of blood in the artery. So this is where our average value of a function formula can help us. So, um, so again, we're trying to compute the average velocity, and let's denote that by v bar, since we're using the variable b to represent velocity, and that average velocity is simply going to be the average value of this velocity function, right, over the interval from 0 to capital R, right, because x has to fall between 0 and capital R. So our interval that we're calculating the average velocity over will be from 0 to capital R. So remember, our average value formula says what? We take the length of that interval, so that's going to be 1 over capital R minus 0, and then we multiply that by the definite integral, right, from 0 to R of our velocity function. which is going to be k times r squared minus x squared. All right, so let's see if we can carry out this this integration and compute the value of this definite integral. Of course, the value that we get at the end is going to involve some symbols, right? Because we have these constants, unnamed constants k, well, named constants, but at least they're not assigned values, k and capital R squared. All right, so let's see. Of course, r minus 0 is r, so I have 1 over r times the integral from 0 to capital R of, let's expand this product, so I'm going to write this as k times r squared minus k times x squared, and of course we're integrating with respect to x. Well, now we have two terms in our integral, right? So I can integrate those two terms separately. So I have 1 over r times, and now let's go ahead and carry out the integration. So notice this term is a constant in terms of x, right? Because x does not appear in this term. So this is really just a constant. So when we integrate k times capital R squared, we're just going to get k times r squared times x, right? Now when we integrate this term, of course, this is not a constant, but we can integrate this using the power rule, and that integrates very easily, right? That's just going to be add 1 to the exponent and divide by the new exponent, so we get k cubed over 3. And don't forget, we're evaluating this from 0 to capital R. So I get 1 over r times, let's see, what do we get now? Well, when we evaluate this at capital R, right, we're going to get k times r squared times r, because I'm going to substitute r for x, right, minus k times r cubed over 3. And now, when I evaluate it at 0, that's exceptionally easy because both terms contain x, right? So that means when I substitute 0 for x, all the terms are going to disappear. So when I evaluate this at 0, I'm just going to get 0. Ooh, nice, right? Okay. All right, let's see now if we can simplify here our result a little bit. So I have 1 over capital R times k r cubed minus k r cubed over 3, right? So I guess that would be 1 over r, and then kr cubed minus essentially 1/3 kr cubed is going to be 2/3, right, of k r cubed. Right? Here you have 1 kr cubed minus 1/3 kr cubed, and that's going to leave you with 2/3 kr cubed. And you're multiplying by 1 over r, so we're going to be able to cancel one of those factors of r. So it looks like I'm going to end up with 2k r squared over 3 as my average velocity of the blood through that blood vessel.